Hello everybody. In this video we're going to talk about the topic of what is science. So astronomy is a natural science and this is a general education science course. We should spend a little bit of time talking about what science itself is, since that's what we're going to be engaging with in general all semester, although we'll be doing the science of astronomy. So what I'm going to do is I'm going to run through these batch of slides, and then the next video I'm going to give you a practical application of how we go through the scientific method. So what I'm hoping to do is to actually give you a view of what is science from a practicing scientist standpoint. How do I view science? And then of course we have to go over some of the fundamentals, like what is a theory, what is a hypothesis, the stuff that you've heard about and can be kind of bland and dry, but hopefully I'll liven it up a little bit. I want to start this idea about what science is and what science is not. There's sort of this growing prevalence of this idea that if we have all the data out there, that science is just a huge collection of facts. And if we had all the facts, then that's it, we've done science. So this idea that science is just facts that you can recite off or quickly look up, no, that is not what science is. Science is much more than just facts and data. There is a lot of creativity and innovation that has to go into coming up with explanations about how the natural world works, and then being able to back up your ideas, your explanations, with experimentation, observation, and data that is collected. And just to kind of hammer this point in that science is not just a collection of facts, let's consider this imaginary scenario where we have all the observations and all the possible measurements of every possible event and every single thing in the universe. We have a complete set of facts about the universe. So we have all the facts. Of course, this is not a real possibility, but it's an imaginary scenario. So we have all the facts about the universe, every event over all time, and everything in the universe. So I ask the question that if we have all the facts that are available in the universe, do we understand the universe? Is that collection of facts understanding of the universe? And you might not even have to think about this one too long before your brain screams, no. Just because we have all the facts doesn't mean that we understand the universe. We don't understand nature. So what are we missing? We're missing the understanding of how things work. We're missing the explanations that connect between all the facts that tell us why those facts are the facts that are out there, why that data is the data that we observe. So we're missing the physical explanations of what explains how natural phenomenon actually operate. And if you understand how the natural phenomenon actually operate, then those facts that we observe should be explainable. So we're missing really the how of it. And it's really the how, the explanations, the understanding of how the universe works, that's what science is. It is not just listing facts or stating facts. It is the connection between the facts. It is the how of it. So how do I approach this? What do I look at? And I'm going to take sort of an epistemological standpoint on this one. Science is a branch of philosophy technically, so I will borrow from philosophy, and I will go with science is a system of knowing. It is how we know things about the natural world. So science is a systematic effort to understand the natural world, and what it's going to do is it's really going to provide the how of things. It's going to give us those explanations of how a natural phenomenon operates. And within those explanations, we're going to be able to make predictions based on the explanation itself. We'll be allowed to predict how a natural system will behave in the future. So we can actually predict with high degrees of accuracy and precision to tell you how things will behave in the future. So it is a system of knowing that provides explanations for how natural phenomena in the universe work. Not why. Science is not in the business of doing the why questions. We're into the how questions. The why questions are much more of the philosophical realm. As a science, we rely on observation and experiment to gather what we call empirical evidence. So we need to go out there and observe nature, and then we need to come up with ideas of how to test nature, how to test our ideas of what explain our observations. And we're going to do that by collecting data. And that's really what we're talking about when we say empirical evidence. That's just our observation and measurements that we're making. And what makes empirical evidence different than just non-empirical evidence is that these observation measurements can be confirmed by further observation and experimentation by anybody. So it's evidence that can be confirmed by measurement and observation. Colloquially, you might want to just call this data, scientific data. And then what we're going to do is we're going to use that empirical evidence to generate ideas, have ideas, potential explanations of how a natural phenomenon works, our scientific hypotheses, which will provide us a prediction. So we can design into a scientific experiment to test that prediction of how, if nature works by how the hypothesis says, then we should observe blah. So we design an experiment to see if we observe blah or not blah. And then eventually we'll have these grand sort of larger explanations of how nature operates in general. And that's where we're building up into the idea of scientific theories. So hypotheses and theories are both describing how a natural phenomenon will work, and they need to provide predictions for how nature is going to behave. The key is predictions, and they have to be testable predictions. And of course, science is going to follow the scientific method. It's sort of our user's guide of how to do science. It's a lot messier than just the simple prescription, but I'll get to that at the end of the video. I've said a lot of this already, and I know I'm going a little bit more through the slides here, but I really want to hammer in the importance of just the basics of science. We should be very, very careful. So if we're going to be doing science, it has to follow some basic tenets of science. If whatever we're engaging in to explain how nature works does not follow these tenets, you can't call what you're doing science. So these are requirements for something to be called science, to be actual science and to be engaging with the activity of doing science. So the tenets of science. It must be explanative, and that means that it's going to have predictive power. So whatever you're doing, it must have a clear hypothesis, a clear explanation of how something is going to work with a prediction of how nature will behave given a set of circumstances. So it's an explanation that predicts. And of course, you have to give an explanation of, or you have to provide what circumstances that this explanation works under. So it must also be testable. So what we call testability or verifiability. So our hypotheses with prediction, that prediction must be testable. So any hypothesis or theory must be testable or verifiable by the scientific method. So you can come up with these grand ideas, these explanations for how nature might work. But if it can't provide a testable prediction, something that you can actually go out to see and test whether your idea is right or not, you are not engaging in science. Sorry, string theory. But you are not really providing us testable predictions. This is also one of the problems with multiverse theory right now. The mathematics of scientific, a lot of our scientific theories about how nature works, our laws of physics, our understanding of physics, can predict that multiple universes can exist. But currently we have no way of actually designing an experiment to test whether or not those multiple universes exist. So yes, scientifically leading, but not quite yet science yet, since there's not the testable or verifiable part. People are starting to come up with some clever ideas, so multiple universes are starting to enter the realm of testable and verifiable. Falsifiability. You'll get it right eventually. So any explanation of science must be falsifiable. That means it can be shown to be false, that whatever our idea is, no matter how long we've been using that as our explanation of nature, it can be shown to be false. And this can be from a single new piece of evidence or a new idea that comes along. So the way I like to put this is, in science, we're never 100% certain about anything. And I'll give you a little bit further explanation about that. We are not in the business of proving things. Science never proves anything. So anytime you read an article where it says science proves, what you're really seeing is somebody doesn't fully understand science. We do not prove things. What we do is we provide explanations that best fit the data that we have, that best fit our observations. And we're going to tell you how confident we are that our explanation is right. We are going to qualify and quantify our ideas, and that quantification is never 100% certain. If you're 100% certain about anything, you can't show it to be false, and you're no longer doing science. You're more in the realm of dogma at that point. So how do we actually go about doing that? If we're not 100% certain, we want to say that we are as close to 100% certain of our findings as possible. So in a quantitative science, we're going to assign a level of certainty. How strong are we, or how confident are we that our answer is correct? So we will, if we're going to use an example of a number, we will give you a number and then a little bit of wiggle room, a little bit of plus or minus. And that little bit of wiggle room, that plus or minus, like here's our answer with some wiggle, that wiggle room is called uncertainty. And I'm going to actually do an example of this here in a moment, but the example we're going to use is the age of the universe. I talked about this in one of the other videos, that we have this number 13.798 plus or minus 0.037 billion years as our age of the universe. That plus or minus 0.037 billion years, 37 million years, is our uncertainty in that answer. And we will assign a certain probability associated with that level of uncertainty. How confident are we? And I'll show you that with some examples. The final tenet of science, all science must be repeatable. So any experiment, observation, any conclusions that are reached, somebody else has to be able to go and do the same experiment design, follow your prescriptions of how you did the experiment, and reproduce your results. You can't just do an experiment once and go, that's it, that must be the right answer. It has to be verified by repeatedly doing the experiment over and over and over and over and over and over again. So repeatability. Now, since it's the hardest part, I think, for you to start wrapping your brains around, but it's also a core part of doing science, this fact that we are never 100% certain, I want to really spend some time digging into how we quantify our degrees of certainty and what kind of terminology we have to use when we're talking about looking and analyzing the empirical evidence that we get so we can test our hypotheses. So we are going to assign a level of certainty, and we're going to use a set of language around it so we can actually know what we're talking about. And the first part I want to address is this idea of accuracy and precision, two ideas that are usually conflated with one another and thought to be the same. So let's start with accuracy. And we will use the common example that people use of a dartboard. So let's say that the goal of the game of darts that we're playing is to hit the bullseye. So an accurate trial, so a trial here being a throw of a dart, would be one that hits the bullseye or falls very, very, very close to the bullseye. If we were trying to hit the 20 on a dartboard, and maybe you want a triple 20, which would be about here, if that's what your goal is, if that's what you're aiming at, if you put the dart there, then you are accurate. So accurate is how close you are to the true answer, whatever the true answer is, which we can't know what the true answer is because that would be 100% certainty. So that's what accuracy is. It's just how close are you to your target? How close are you to the true answer? Precision requires more than one trial. You have to throw more than one dart before you can talk about being precise. So precision is talking about if I repeatedly throw darts, how close or how far do they spread out from one another? Are they all clustered together, high precision, or are they spread out, low precision? And then we can quantify that precision. How much on average do the darts that you throw, how far away are they from one another? You could actually assign a value to that, and that's what we call our uncertainty. So let me walk you through some examples of this, of both high accuracy and low accuracy, high precision and low precision. So this example of a dartboard, I'm throwing 5 darts in each one of these examples, and these blue crosses indicate where the darts land. So this would be, they're all very close to the bullseye, that's my goal, and they're all very close to one another. Each dart throw doesn't really differ from where it landed by much. So we call that high accuracy and high precision. We hit the bullseye and all the darts were very close to the bullseye. Here is an example. Again, the game is to hit the bullseye, but I missed the bullseye. I wasn't very accurate with my dart throws here. I consistently missed my target. I was off from the true value, saying that the bullseye is our true value that we're aiming for. However, every one of my darts still clustered together. Each dart throw did not vary in its position very much. So this would be an example of low accuracy, but still high precision. And this is where things get a little bit trickier, because we never just use a single data point, we use multiple data points. And what you want to do whenever you're evaluating your accuracies, you want to look at the average of all the data that you collected on some thing that you're observing. So here, I throw 5 darts, and I hit right in the bullseye, and then I hit here, 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 and here. If I were to average the position of all of these darts, it would be right on the bullseye. So that would be, in the aggregate of all my throws, I hit the mark. I hit the bullseye. My average toss would land in the bullseye. So that would be high accuracy, but every dart is very, very, very far away from one another, so low precision. Each dart varied by a large amount from where the previous one landed. And that leaves us with, I'm just not very good at darts. I kept chucking them at the dartboard, hit one here, hit one here, hit one here, hit one here, hit one here. None of them really went close to the bullseye. I could average them all together, and the average position would not be close to the bullseye. So that's low accuracy, and each one landed far from every other one, so low precision. So hopefully that really helps you understand accuracy and precision. What I want to give you now is an example of how this might work in science. And our goal is to measure the age of the universe. We don't know what the true age of the universe is, but we can collect a lot of data that can be translated into an estimate for our age of the universe. And that's in the previous video, I gave a link to the article that gives us this number, that the age of the universe, our best estimate right now, is 13.798 billion years old, gigayears, plus or minus 0.037 billion years. And that plus or minus, so that plus or minus right here is our uncertainty in the answer. It's telling us that, hey, there's a little bit of wiggle room, that the true age of the universe will fall between this range of values. And then we can assign a level of confidence to it. And the way that this works, if you're curious and a stats person, what I'm about to talk about is standard deviation. But if you don't want to pay attention to that, you can pop it out of your brain. Notice the green text here. So this is basically saying, with this wiggle room right here, our precision in measuring the age of the universe, that we are 68% certain that the true age of the universe is within this range. So let me go and work that out, of 13.761 to 13.835, billion years old, not G-Y-R, giga years. So we're 68% certain it's within that range. That's not very certain. I mean, a coin toss is 50% certain you're gonna get the right answer, right? So what we wanna do, if we wanna say that we have higher confidence, we can double this uncertainty. So I double the uncertainty, multiply 0.037 by 2. And if I do that, then I'm 95.5% certain that the age of the universe is 13.798 plus or minus 0.074 billion years. So now I have 95% certainty in the range around my answer. Triple the uncertainty, so triple this number, and you get plus or minus 0.011. And we would be 99.7% confident that the true age is within that range. So you can see, yes, there's a larger range, but because there's a larger range now, we can be more confident that the real value, the true value, falls within that range. And go ahead and skip the 4 times. We'll go to the gold standard for most sciences, what's called 5 sigma certainty. So 5 times this plus or minus one that's listed right here is 0.037. That'd be plus or minus 0.0185 billion years. And at this point, we are 99.9999% confident that the age of the universe would lie between 13.613 and 13.983 billion years old. That is very, very, very high confidence. Not 100%, but very, very high confidence that we have nailed down the age of the universe. It could be over here. It could be closer to the 13.6. It could be closer to really the 14 right here. So hopefully that gives you a little bit of information about how all of that, how uncertainty works and how we report things in science and the fact that we are never 100% certain. I do want to go ahead and give you a little bit of explanation about some of the common terminology that is associated with doing science. What is a scientific hypothesis, theory, law, and experiment? And I really I need to be sure I say it. When we say hypothesis or theory, we're not using the colloquial sense, which in both cases translates to, yeah, it's a pretty good guess. I'm just spitballing an idea here. When we say scientific hypothesis and scientific theory, we mean something, especially whenever we say scientific theory. Scientific theory is the weightiest thing we can say in science. So what is a scientific hypothesis? A scientific hypothesis is we don't know how nature works yet, but based on the data that we have, here is an idea, a proposed explanation of how a natural phenomenon is going to work. And that proposed explanation will give us a clear testable prediction if our explanation is true. So a hypothesis is really a prediction based on how nature is going to operate. And then we can go design an experiment and test it. A scientific theory, however, is an explanation. It's this grand unified explanation of how some aspect, some large swath of the natural world actually operates. It is the explanation part, and it's weaving a lot of different ideas together into this cohesive understanding of how nature is operating. To be a scientific theory, you have to be expansive, you have to be explanative, and you have to have survived a battery of tests. And you have to be repeatable over and over and over. And oftentimes they'll make predictions that go beyond just what they were designed. So general relativity will predict some pretty wild things out there. And slowly but surely, we've been developing technology and experiments to test if those predictions work, those hypotheses that come out of the theory of general relativity. And so far, every one confirmed. If one of them wasn't confirmed, then we have to revisit the entire idea of a theory because the theory is falsifiable. So our theories are comprehensive explanations of how nature works. They can contain multiple hypotheses. They give birth to new hypotheses. They are the weightiest thing that we can say in science. They are grand explanations of how nature works. And they're supported by volumes of evidence that's usually collected over decades to centuries. Another common thing that people see and get confused about is a scientific law. It's not a law in the fact of you must obey. A scientific law is really saying it's just a codification of what's going to happen given a set of circumstances. So yes, it has predictive power and it provides you some explanation of how nature is working. And it has some overlap with a theory and a hypothesis there, but it's a little bit different. Because usually these scientific laws, this codification, how is it codified? It can be given in the form of an equation. So these are already supported by evidence, and they're leading more towards describing what will happen, so they're giving a prediction of what will happen rather than really providing an explanation, which is more what a theory does. And what is a scientific experiment? That's just what we're going to design. It's our set of procedures that provide a very, very carefully controlled environment so we can make our observations and have high confidence that the data that we are collecting, our empirical evidence, is both accurate and precise. So it has high accuracy and high precision. And then we can use that high accuracy and high precision, that data set, that empirical evidence. The better the accuracy, the better precision, the better we can test our hypotheses. So that's what a scientific experiment is. It can be in the lab. So you can picture a chemistry experiment where people are actually mixing things in beakers and doing your titrations and things like that. It can be an experiment of a set of objects that I would like to observe. So I can collect the data from, say, a bunch of asteroids because I want to test some idea I have about asteroids. It can be a physics experiment. It could even be a computer model. That is a form of experimentation, computer modeling, where we can put in physics that we know and see what comes out to test whether or not we have a comprehensive set of ideas of physics that go in to really accurately describe a natural phenomenon. And I want to just really hammer in that scientific theories are the strongest statement that we can make about how some grand idea of nature operates. So we're talking about our relativity, our quantum theory, our theory of natural selection and evolution. These things that have withstood decades to centuries of evidence and provide these big explanations of how some broad part of nature works. So a theory must fulfill all the tenets of science, obvious, meaning it has to be explanative, provide predictions that are testable. It could be falsified even by a single new piece of evidence, and they have to be repeatable. But really what I want to talk to you about with the theories are sort of the more esoteric qualities of it, the shoulds of it. And shoulds can be a dangerous word right here, but a scientific theory should be simple. And this is that concept of Occam's razor that you may have heard of. So let's imagine that we have two explanations of how a natural phenomenon works, and they give equivalent predictions. So we have two explanations that allow us to predict what's going to happen in the future with the same degree of accuracy and precision. But they're fundamentally different explanations. One of them is horribly complicated. The other one is simple. Occam's razor say adopt the simple one, ignore the complicated one. So they should be simple. You should be able to apply Occam's razor. And then there's the scientific theories should be elegant. There should be an oh wow factor attached to them. By understanding and looking at a theory, there should be a moment where you're just like, holy cow, I cannot see the world around me the same anymore. Something has fundamentally changed, and now I have a deeper understanding of the natural world in a very profound way. And I really just need to hammer in that scientific theories have mountains of evidence, survived a battery of a variety of experiments from different approaches, and all of the experiments and the evidence to date has supported those theories. All the predictions have turned up to be right. So not saying that they are we're 100% right and we're proving it, but we have shown that our predictions are correct with a certain confidence. So they also have tremendous predictive power, and they really will go beyond what is currently known and allow us to come up with new discoveries, ideas that we did not have before. So they really are what push us into the future of innovation. And if you think about it, scientific theories, things like this, these grand explanations, that requires a lot of creativity and innovation. People often think that science is this really dry and boring thing that is full of non-creative people. To do science and to do science well requires a tremendous amount of creativity to come up with these explanations of how nature works, and then to come up with ways to test whether those explanations work, sometimes by building the most ridiculous pieces of scientific equipment like the LIGO facility or the Large Hadron Collider. That is a accelerator where they smash particles together. And yes, on occasion, scientific theories are overturned. And this is not like, oh, you dumb scientists, you were wrong. That's not what's happening when we overturn one of these. What a overturning of a scientific theory in the science world, those are called scientific revolutions. And these are celebrated by scientists. A quintessential example of this is this Newtonian view of what gravity is was superseded by Einstein's general relativity. And we still use Newtonian gravity to do a lot of work because it provides predictions, it provides answers that are accurate, but have slightly less accuracy and less precision than general relativity. And general relativity allows for a whole slew of other predictions and a better, deeper understanding of nature. So these scientific revolutions, when a scientific theory is overturned, it's really bringing us into a new age of understanding of the universe around us and the natural world. So with a scientific method, just going to briefly mention this in my next video, I'm actually going to run you through a process of testing one hypothesis versus another, what I call Galileo versus Aristotle. But typically, just to sort of run you through the process, is you have some observations. Maybe you're meaning to make them, maybe you weren't, maybe you found a data set you found interesting. So you have these observations, you look at it and you go, huh, that's pretty interesting. I have an idea that might explain why the observations are that way. Then at that point, you're forming a hypothesis. So you form your hypothesis, an explanation of how nature works. You go, okay, if this is true, it will predict that this will happen under these sets of circumstances, which allow you to design your experiment. Your experiment gives you new observations, new empirical evidence. You look at it to test your hypothesis. Sometimes it fails to confirm your hypothesis. Sometimes it confirms your hypothesis. If it fails, you're not like, well, this was just a waste of time. No, you learned something. And from what you learned, it allows you to re-look at things with the larger volume of evidence that you have now to come up with a new explanation, a new hypothesis to perform new experiments. So yes, the failure here should be celebrated. And then sometimes you confirm your hypothesis, which then can lead to new ideas. You have more observations now. You can come up with new hypotheses about how that part of nature works. Maybe you're building a grander explanation and on your way towards establishing a scientific theory, which with new observations, you can come up with new hypotheses, start weaving together a larger explanation. So you can just always loop back up. And of course, this is where your practical applications, this is what we'd call technology, is an offshoot of all of this. So notice that this is a never-ending loop. You never actually reach an endpoint. Science is a continuous process where typically when we answer one question, it gives birth to 10 new questions. They're just making up a number 10 there. So science is expanding. There is so much left to discover out there. All right, I know this was a long video about science. I hope you enjoyed actually hearing about science talked about from a scientist. I hope you learned something a little bit different. And I will see you when we actually run through a example of how the scientific method works.